Okay, thank you, Heiko. So in the last part of this lecture, we'll talk about the steps of representational similarity analysis one by one. The first step is to choose and use an RDM estimator to actually get an RDM, a representational dissimilarity matrix, from our data. The second step is to choose an RDM comparator in order to quantify the similarity between different representations. And the third step is model comparative inference, where we compare different models as models of a representation in a brain region so that we can learn something about the computational mechanisms underlying the representations in biological brains. So let's start with step one, estimating representational geometries by computing an RDM. We have to choose a distance estimator. So first, let's quickly recap what Heiko has already told you. We need to take correlated response pattern noise into account to make distances reflect the discriminability or the decoding accuracy for a pair of stimuli. If we use the squared Euclidean distance naively, we could have this case where we have a large Euclidean distance, but displacement between the two patterns is in a direction in which the noise is very large as well. So the stimuli are actually quite confusable. If you were given a response pattern from one of these two distributions and you were supposed to tell what the stimulus was, you'd make a lot of errors because these distributions are very overlapping. And even though this is the longest of the three Euclidean distances here, it's also the most confusable pair in this simple example. And as Heiko mentioned, a remedy for this is to whiten the space by applying a linear transform that renders these Gaussian distributions isotropic. And after doing this, we can use the Euclidean distance. And when we use the Euclidean distance after this whitening linear transform, that's actually equivalent to a different kind of distance, which is called the Mahalanobis distance, where you have the inverse of the error covariance here in between these two pattern differences, and that achieves this whitening transform. The second important consideration in estimating distances is that distance estimates from noisy data are positively biased. So one very quick way to understand this is to think of the case where two stimuli elicit exactly the same true activity pattern. So the true distance is 0, but now we get these noisy estimates of both patterns. And when we compute, for example, the Euclidean distance, of course, by definition, that's positive. So we're always going to overestimate this truly 0 distance. And that's this positive bias. And this positive bias affects distance estimates in general when we naively apply distances in order to estimate distances from noisy data. So let's think this through in a little more detail. We have two response patterns here, Ri and Rj, and these are the true noise-free response patterns. So we would like to estimate this true distance, the length of this gray line, Dij. However, we don't have access to these true response patterns. We just have measured brain activity data. So we have estimates that are affected by noise. And in a high-dimensional space, if the noise is isotropic, I'm assuming that here just to illustrate this, these error displacements that our pattern estimates are affected by will be approximately orthogonal to each other and also orthogonal to the connection line between the two true patterns. So in this scenario here, where we get a distance estimate from our pattern estimates that is longer than the true distance, and it's longer by a very predictable amount. So it's just, since these elements are approximately orthogonal to each other, the norms of these errors squared and the true distance squared just add up to give us our squared Euclidean distance estimate. Here I've simulated this. I generated some random patterns of different true distances. Then I added noise, and I'm plotting the true distance, so the one the Euclidean distance without the noise versus the Euclidean distance with the noise. And unsurprisingly, we see this positive bias. So all of the points are above the identity line here. And it's particularly serious for the case when the true distance is very small. Note that here what I'm plotting is actually the distances, not the squared distances. If I plotted the squared distances, then you'd see just a shift and you wouldn't see this nonlinear effect. So here's another example where we have different true distances and in different shades of gray. And you can see that we only get the right estimate with a naive distance estimator, here the squared Euclidean distance, when the noise is 0. And as the noise goes up, we get a stronger and stronger inflation of the estimated distance. So what do we do? Well, we can remove the distance estimation bias. And how do we do that? We can use different data sets for these pattern differences before and after the inverse of the noise covariance. And to understand this a little bit better, we can remember that the first part of the definition of the Mahalanobis distance here is also the definition of the Fisher linear discriminant. So this is a vector W that we can project the data on in order to distinguish these two distributions of response patterns efficiently. And what we do in the so-called cross-Nobis distance estimator, which is short for cross-validated Mahalanobis distance estimator, is we take a separate data set and we have estimates for the two response patterns, Ri and Rj, from the separate test data set, and we project them onto the Fisher linear discriminant estimated with our first data set. And this is a way of removing the bias. When we plot the estimated distances as a function of the noise, you see for different true distances shown in different shades of gray here, you get on average the true distance, even though, of course, as the noise goes up, the variability becomes larger and larger. There's nothing we can do about that. If there's more noise in the data, our estimates will be more variable, but on average, they'll be correct, and that's the definition of unbiasedness. So in tutorial 4, you'll play around with different ways of estimating distances. You'll learn about the Mahalanobis distance and how to whiten the space, and you'll also learn about removing the bias inherent to naive distance estimates. So let's move on to step 2 of RSA, which is choosing and applying an RDM comparator. So this is about quantifying the similarity of representational geometries by comparing different RDMs. The question is, what do you compute? How do you quantify how similar two RDMs are? An important issue in this context is that we need to account for dependency among dissimilarity estimates by whitening. Now, this might seem familiar. We just talked about whitening in the context of response pattern variability, noise in the space of the neural responses. Now we're talking about noise dependency in the space of RDM estimates. So we're talking about the space that the RDMs live in. So this space has one axis for each dissimilarity, so one axis per pair of stimuli. And a point in this space is an RDM. So here's an example where we have a data RDM D and two model RDMs M1 and M2. And if we naively selected the model that's closer to the data in terms of Euclidean distance, we would select model M2 here because it's closer in a Euclidean distance sense to the data RDM. However, when we consider the covariance of the RDM estimation error, we see that model 1 actually has the higher likelihood. So the probability of the data given model 1 is higher than the probability of the data given model 2 because the variability of the uncertainty about the the actual RDM given a model is not isotropic. We can deal with this in the same way as at the level of the neural responses by whitening. So we can perform a whitening linear transform that renders these RDM estimation error distributions isotropic. And after doing that, we can trust the Euclidean distance or other simple ways of comparing RDMs, such as the cosine similarity or the Pearson correlation coefficient. So after we do this, we end up correctly choosing model 1 here as the better model for explaining the representation in this data set. And this has been worked out, so we know how to estimate this dissimilarity estimation error covariance by W1D3 and Heiko Schütt, and it's implemented in our open source Python toolbox, so you can check it out there or play around with it in the tutorials. So this gives us whitened RDM comparators, and there's a little more under the hood, so we can use this knowledge about the covariance of the RDM estimates in different ways. We can use it in the context of biased RDMs. For example, we can use biased RDMs and the cosine similarity, and this turns out to be equivalent to the linear-centered kernel alignment, which is a popular way of comparing representations in machine learning. But it's more general than that. So we can also use the Pearson correlation in the context of biased RDMs, or we can use unbiased RDMs, so these unbiased cross-validated distance estimators, and then use the cosine similarity or the Pearson correlation and have whitened RDM comparators for this context. All right, let's talk about step 3. Step 3 is model comparative inference. So now we're talking about statistical inference comparing multiple neural network representations as models of a brain representation. So we want to compare these models. We think maybe some models that are better models of a representation in the brain than others. And we hope through these comparisons to gain insights into the computational mechanisms underlying brain computations. So when we make predictions from neural network models, we often want to fit some parameters. For example, we might not be sure, given a model representation with a set of tuning curves, how prevalent these different tuning curves are in the neural population that we've measured. So some fitting is often desirable, and where there's fitting, there's overfitting. And so in order to prevent the overfitting from biasing our performance estimates, we have to do cross-validation. So we designate a set of fitting stimuli and a set of test stimuli, so two disjoint sets of stimuli, and we also designate two disjoint sets of subjects, the fitting subjects and the test subjects. And then we fit our models using only the fitting stimuli and only the dissimilarities estimated from fitting subjects. Then our models are ready for predictions, and they make predictions for the test subjects RDM for the test stimuli. So the models must generalize simultaneously across subjects and across stimuli, which is a hard generalization challenge. And we can do this in cross-validation to get unbiased estimates of model performance. So it's good to have these unbiased estimates of model performance, but we still need to also estimate our own uncertainty about these estimates. And therefore, we wrap bootstrapping around this cross-validation procedure. And the bootstrapping is also two-factor bootstrapping. So we bootstrap resample the subjects as well as the stimuli in order to simulate how variable our estimates would be if we repeated our experiments for different random samples of subjects and stimuli drawn from the same distributions. So the model comparative inference uses two-factor cross-validation to avoid overfitting to either subjects or stimuli, and it uses the two-factor bootstrap wrapped around the cross-validation to treat both subjects and stimuli as random effects for the purposes of inference. And we think that this way we can get model comparisons where when one model is significantly better than another model, we can actually trust that. We can think that if someone replicated our experiment with a different sample of subjects and a different sample of stimuli, then they might get the same result. So the model evaluation gives us something like this bar graph, which shows the performance of different models as representational models of a reference representation, for example, from a brain. This is simulated data, but this is what it looks like when you compare different predicted RDMs to brain RDMs measured in subjects. And what is plotted here is the RDM prediction accuracy, and here it's the mean across the subjects of the Pearson correlation between the predicted RDMs and the measured RDMs. Importantly, we get these indications here of significance. So at the top here, you see what we call Golan wings, which show the significant pairwise differences. So this is an exhaustive summary, visual summary of all the possible pairwise model comparisons. And the way this works is you look at the dot here, that's the reference model. So this would be FC6 in this case. And then there's a little tick mark for each other model that this reference model significantly dominates. So it significantly dominates conf5 here. It doesn't significantly dominate FC6, but it does significantly dominate FC8 in this case. And then importantly, here's the noise ceiling, which has an upper bound and a lower bound, and it gives us an estimate of the range in which we would expect the true model, if it were one of our models, to fall in terms of performance, given the noise and the intersubject variability in our data. Below the lower bound of the noise ceiling, we have these dewdrops here, which indicate significant tests against the lower bound of the noise ceiling. And you can see that these dewdrops are present for all of the models. So all these models fall short of explaining the data, except conf2 here has evaporated this dewdrop because it comes quite close to the lower bound of the noise ceiling. And we also have these dewdrops on the line at the bottom here indicating significant tests against chance performance, which is a very low bar. And all models here explain significant variance in the data RDM in this case. In tutorial 3, you're going to dig a little deeper on statistical inference on representational geometries and try out our toolbox for this purpose. So a take-home message is that we can compare neural network models in terms of their ability to explain the representational geometry of a brain region. And that's an important tool for computational neuroscientists to learn about computational mechanisms of biological brains.